Mathematics emerged as a means to quantify our world, enabling the measurement of land, predictions of planetary motions, and tracking of commerce. However, a seemingly impossible problem arose, requiring a detachment of math from the real world. This led to the separation of algebra from geometry and the invention of new numbers so extraordinary that they came to be known as imaginary. Ironically, these very numbers would later find a central place in our most advanced physical theory of the universe. By divorcing mathematics from its ties to reality, we unearthed the true nature of reality itself. Light music. In 1494, Luca Pacioli, Leonardo da Vinci's mathematics teacher, published Summa de Arithmetica, a comprehensive summary of all known mathematics in Renaissance Italy at that time. One section dealt with the cubic equation, which today we would write as ax cubed plus bx squared plus cx plus d equals 0. For thousands of years, civilizations such as the Babylonians, Greeks, Chinese, Indians, Egyptians, and Persians had attempted to find a general solution to the cubic equation, but all had failed. Pacioli concluded that a solution was impossible. This conclusion was somewhat surprising because without the x cubed term, the equation reduced to a quadratic, a problem that many ancient civilizations had successfully solved. Today, we learn the general solution in school. X equals minus b plus or minus the square root of b squared minus 4ac, all over 2a. However, most people merely plug values into this formula without understanding the geometry that ancient mathematicians employed to derive it. In the past, mathematics was conveyed through words and images rather than equations. Let's consider an example equation. X squared plus 26x equals 27. Ancient mathematicians envisioned the x squared term as a square with sides of length x, and the 26x term as a rectangle with one side of length 26 and the other side of length x. The combined areas of these shapes equaled 27. So, how did they determine the value of x? They would have the 26x rectangle, creating two 13x rectangles. By positioning these two rectangles to form a nearly complete square, they could identify the missing section, which was a 13 by 13 square. To maintain the equation's balance, they added 169, the area of the new square, to both sides. Now, they had a larger square with sides of length x plus 13, equal to 196. Taking the square root of 196, they found that x equaled 1. This visual approach was an effective way to solve quadratic equations. However, it had limitations. If we examine the original equation, x equals 1 is a valid solution, but so is x equals negative 27. For ancient mathematicians, negative numbers did not exist because they primarily dealt with real-world quantities such as lengths, areas, and volumes. A square with sides of length negative 27 had no practical interpretation. Consequently, negative numbers were not recognized. Mathematicians had such an aversion to negative numbers that instead of having a single quadratic equation, they employed 6 different versions that ensured the coefficients were always positive. A similar approach was applied to the cubic equation. In the 11th century, Persian mathematician Omar Khayyam identified 19 different cubic equations, but again, he worked with positive coefficients only. He managed to find numerical solutions by examining intersections of shapes like hyperbolas and circles, but his ultimate goal of a general solution remained elusive. Khayyam stated, "Maybe one of those who will come after us will succeed in finding it." Fast forward 400 years and 4,000 kilometers away, progress on the cubic equation was being made in Italy. Mathematicians such as Scipione del Ferro, Tartaglia, and Cardano made significant contributions to the field. Cardano, in particular, published a method for solving the general cubic equation in his book, Ars Magna, in 1545. However, Cardano's method involved the use of imaginary numbers, which were seen as nonsensical and lacking any practical interpretation at the time. Imaginary numbers were first introduced by the Italian mathematician Raffaele Bombelli in his work, L'Algebra, in 1572. Bombelli used the term imaginary to refer to these numbers because they did not have a direct representation in the real world. He considered them to be fictitious or imaginary. Imaginary numbers are defined as multiples of the imaginary unit, I, where I is defined as the square root of -1. Despite the initial skepticism surrounding imaginary numbers, mathematicians recognized their utility in solving complex equations. The German mathematician Carl Friedrich Gauss further advanced the understanding of complex numbers in the 19th century. He established the foundation for complex analysis, which deals with functions of complex variables. Complex numbers, which combine real numbers with imaginary numbers, are now widely used in various branches of mathematics, physics, and engineering. They have applications in electrical engineering, signal processing, quantum mechanics, and more. The beauty of complex numbers lies in their ability to represent and manipulate quantities that involve both real and imaginary components. Moreover, the concept of imaginary numbers led to the development of complex plane geometry, where points on a plane are represented by complex numbers. The complex plane provides a geometric interpretation of complex numbers and allows for the visualization of mathematical operations, such as addition, subtraction, multiplication, and division. In the realm of physics, imaginary numbers play a crucial role in describing phenomena such as alternating currents, quantum mechanics, and the behavior of waves. For example, in quantum mechanics, wave functions are represented by complex numbers, and the imaginary unit, I, appears in the Schrödinger equation, which describes the evolution of quantum systems. In summary, the evolution of imaginary numbers represents a significant shift in mathematics, where the abstract and seemingly unreal concepts find practical applications in understanding and describing the world around us. From their initial dismissal as nonsensical to their fundamental role in modern mathematics and physics, imaginary numbers have demonstrated their profound importance in our understanding of the universe.